All right, Dane, you almost ready? I think we're pretty much
Oh
got
yeah,
it on.
yeah. If you see both my screens, you see a blue-green statistics
Yeah.
probability and my
Yep.
ugly fingers.
There you go. And that for those, I'll get it following along. But for those, Dane will have his PowerPoint on one side, and then the if you pin the other one where he does his drawings on, I've been finally figured out how to do it on the Zoom side, so I can zoom in and out when you're on one side to the other, and it actually works on the recording side. So
Okay.
that part's cool. So we'll have to go back. I know we've got to redo one of the sectionalized ones, I think, because we got some holes in that one. So, but let me let one more in, and then I will start. Tonight, we have Dane Courville. Dane began surveying in 2005. He received his land surveying and training certification in 2007, subsequently became a professional land surveyor in the state of Maine in 2009. He's also licensed in Vermont, Texas, Colorado, and Oregon. In addition, Dane has a passion for teaching, which is why he's on tonight and all the 20 other times he's been on. It was through teaching classes for up-and-coming surveyors that he discovered a gap in available education materials. Over many months, Dane took pages and pages of teaching notes and incorporated them into a manual to assist the future surveyors gaining the knowledge necessary to pass the NC's Fundamentals of Surveying exam. The accumulation of his work, the Fundamentals of Surveying Exam Study Manual, is now available to purchase for anyone pursuing a career in land surveying. There's also, we talk about it every time, but there's also videos available that go along with Dane's stuff through the Western Federation, WestFed's website, where you can get about 16 hours of that, and we can get that. So tonight is surveying statistics and ... That was your title.
Yeah. Yeah.
And so for anyone studying the FS, the PS, CST exams, you name it, this should help you get through some type of exam you have going. So I appreciate, as always. I hope you had a good vacation last week, or I guess it's been 2 weeks now in Hawaii, but
Yeah, that was awesome.
ready to go.
I saw some surveyors out there on the North Shore. We went to a few islands, and yeah, it was pretty cool. I stopped and talked to them.
Nice.
I asked them if they were locating a section monument. They were like, "What the hell is that?"
That's awesome.
No, I knew they didn't have them, but I was just pulling their legs.
Mm-hmm.
But it was pretty cool. I kept walking to go get coffee in the morning, and I'd walk by all these houses, and I would kind of do some reconnaissance for some rebar. I was looking for a plastic cap that said Hawaii PLS, blah 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 blah, but
yeah,
I never found one. So
too funny. That's awesome.
No, it was fun. All right, we do have kind of a little bit to cover tonight. This is I have 20 slides, so we'll get through them. But on the NSPS exam, you're going to be provided a exam spreadsheet, which I bring up every time. I'm sorry, not a spreadsheet. Let me see here. Let me grab it for you.
Syllabus, curriculum type. Yeah.
Yeah, it's like let me see. It looks something like this. They call it the handbook, the reference handbook. So I'd highly if you're studying for the exam, go grab this. It's free. It's off NCEES, and you can go and every equation you need to know is going to be on this sheet. They aren't going to ask you to do any math that doesn't have an equation on these sheets. Okay, it's only 12 pages long, and the last 6 pages are probability, standard deviation, which is really not stuff you need to concern yourself with, especially after tonight. But my manual that I wrote, that's essentially what my manual does. It goes through every single one of these equations, and I explain how to use them, why we're using them, and all that. Well, if you notice, let me go find it. There's a section on probability and statistics. So for the NCEES exam, EES, they're going to require you to know this set of equations right here, okay? And that's what we're going to go through tonight. Now, I don't want to minimize the science of statistics, because it's extremely broad. All I'm trying to do tonight is get you familiar with what you have to know for the exam. My a little history on me. My wife's uncle. My wife was born and raised in Maine, on the Canadian border, and she has a lot of family that are Canadians. One of her relatives is her uncle. They live in Halifax, Nova Scotia. And this guy, he's retired, but he was a PhD professor at Dalhousie University and was the leading statistician for the entire country of Canada. This guy was, he still is, absolutely insane with his intelligence. And I'd go visit him, and he'd ask me what I do for a living. I told him, and he was asking me about GPS and RTK, and he was rattling off the statistics and analysis of satellite projections. And this dude knew more about surveying than I ever will, and that wasn't even his field. So I'm just letting y'all know that there's a lot more to statistics than what I'm about to go over, but this is what we need to know for the test. Okay. So that being said, let me get back here. Okay, so the slides are going to go through these 6 operations: definitions, the description of variance versus standard deviation. We're going to go through the types of errors, accuracy versus precision, and then we're going to define uncertainty, tolerance, and accuracy. And then we're going to go through the propagation of error. And I know this is all maybe rocket science, but we're going to get there through the course. Okay. So let's start going. All right. First off, what is statistics? It's the science of assuming smaller or proportional determinations from the analysis of larger sets of data. So you're making a broad statement, or you're making a specific statement based off of a lot of data. Okay. Obviously, the more data that you're introducing into your system, the better your statement can be. So if you, for instance, want to know the effects of a drug on people, and you do your analysis, and you start, and your analysis only involves 5 people, then no one's going to want to take your drug, right? So you want to include 1 million people if you can, so you really get a picture of what's going to happen statistically. So that's the idea. Probability is the value associated with the likelihood that an occurrence will or will not take place. So from your statistical analysis, you can make a statement as to probability. So after you do your analysis, now you can determine the likelihood of something occurring or not occurring. All right. These are the definitions, and as we go through them, you're going to see that they're kind of like a building block. One builds upon the other. Okay. So mean is average. That's there. Those 2 terms are synonymous, mean and average. And all averages is you take the number. You take the value of each data point in your set, add them together, and then you're going to divide by the number of data set points. And I have examples of all these. Okay. The mean, it's not the average, but you're going to get a value that's near the mean, possibly. And what the mean is, it's the middle number in your data set. If you were to organize all of your data set point values in order from largest to smallest or smallest to largest, and you go down and you find the very center or middle value, that is your mean. So if you look at my paper now, let's say we had a data set, and it was, if I had my values listed in order, let's say it'd be like 1, 1, 1, 3, 3, 3, 4, 5, 5, 6, 7. Okay. So here are my data points. And the values are sorted from smallest to largest. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's make it, I want to do this. I'll show you both ways, but okay. Now let's make that a 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 12 data points. I don't have a center of 12, right? So I got to go find the middle two. So that would be the 6 and the 7th. 1, 2, 3, 4, 5, 6, and 7. So these two are my middle. So what I would do is I would take the average of these two, which would be 3.5. So it'd be 7. 3 plus 4 is 7 divided by 2, 3.5. Okay. So my median in this situation would be 3.5. Let's add another one here. So now I have 13 data points, all sorted in order. Now I do have a middle because I have an odd number of data points. So 1, 2, 3, 4, 5, 6, 7. My 7th one is going to be my median. So 4 would be the median in this situation. To find the average of these, I would add up all these numbers and I would divide by 13. And from that, I would have my average. Okay. So median is the center. Average is adding, dividing by the number of data points. Last, we have mode. Mode is what is the most frequent point value in my data set. So in this situation, I have 3 3s. Okay. So 3 3s would be the largest number of a single value I have. So in this data set, my mode would be 3. Okay. So as you can see, they all are different values. If I get an average, it's going to be different than my median, and it's going to be different than my mode. Now, that may not be the case. There might be a situation where they all are the same. Okay. That will depend on the number of points and how accurate your measurements are. Okay. Now, residual. This is a good one to memorize because this is going to come up outside of statistics and other applications too. So what is a residual? So let me find the average of this data set right here. Okay. So I have, it'll be 3, 6, well, let me see. Get my calculator going. 1 plus 1 plus 1 plus 3 plus 3 plus 3 plus 4 plus 5 plus 5 plus 6 plus 7 plus 7 plus 8 divided by 13. My average in this situation is 4.15. My mode is 3. And my median is 4. Okay. So in this case, they're all different. Average 4.15, mode is 3, median is 4. All right. So what is a residual? A residual is how far, let's pick on this guy right here, this number 5. How far is this value from my mean, which is the average? So the residual is how far is any given value from my mean. So in this, with this case, my residual for this would be 0.85 because 5 is 0.85 positive from my mean. Okay. This 8 down here, it would be 8 minus 4.15. This one, my residual for this data point with the value of 8 is 3.85. So what I'm doing is I'm measuring how far is each number from my mean. This 4 is only 0.15 away. Okay. So every single value is going to have its own residual. Now, with those residuals, we can go do other things, which is what I'm about to explain. Okay. Is everyone following me so far? These residuals. Yes.
I was just gonna jump on and say, for those that are maybe just joining in, if you pin Dane's presentation with where he's got the overhead and the paper, if you pin that and his other one, you can slide back and forth and kind of zoom in on those. So just so everybody knows on that. And then Ian threw in the chat real quick, San Francisco Bay, the average depth of the San Francisco Bay is 25 feet. The median depth is about 20 feet and the modal depth is about 4. So it tells you that the deep cut channel and most of the bay is shallow. So that's kind of cool. Thanks, Ian.
Yeah. That's a, I'm going to use that if you don't mind, Ian. That's a good example to stress how things can vary.
Yeah, exactly.
Each one of these has their own purpose. We as surveyors, we tend to lean towards the mean of a data set, but there is a reason and a purpose to have your mode and your median. And it's for that reason right there, because maybe they say, okay, we don't want to include that mode of 4 feet. We know that's, the beach area or something. We want to eliminate that, so they can get your data set with all these measurements and they can eliminate the mode, let's say, to get another different kind of mean. So there's all kinds of different reasons for this. For our purposes, and what we really need to focus on is the mean. Okay. The mean and these residuals, this is basically least squares. Okay. This is how you get a best fit line. If you have a fence and you take 100 shots on that fence for a mile, okay, and you come back and you see points scattered all over the place, they obviously didn't construct the fence in a straight line. Well, now you might be tasked with, where can I put a best fit line in that data set of fence shots that best represents that fence line with a straight line? Okay. And what you're doing through that least squares analysis, you are trying to put that straight line in a location that gives you the smallest residual to each one of these fence shots. That's what least squares is doing. It's trying to put that straight line down all those shots in a location that can best minimize the residuals, which would be the fence shot down to that straight line. Okay. So just keep that in mind. So we know what residual is. Variance. I'm going to show you what variance is. It's the spread of your data points. Okay. So if I go to this next sheet, here's look at this example right here. So look at the red data versus the blue data. All right. So we got all these measurements and we mark them all. Okay. And when we did the blue, let's say, we had values all the way from 0 to 230. So the spread of our data is larger. We have a larger variance with this blue data set than we do with the red. With the red, our variance is only between 65 and 125. Okay. So the spread of our data is what variance is. And if we take the square root of our variance value, then we get our standard deviation. So for standard deviation, the quantity found to determine the range or amount of deviation of a group of measurements. In addition, it is the square root of the variance. Okay. Variance is unitless. Okay. When I'm dealing with variance and all I care about is the spread of data, I just tell you a number. So the variance of this red data set is from 65 to 125. Okay. So my variance in this situation is 60. Now, 60 doesn't have unit. I don't even know what that red data set was measuring. I don't know if it was measuring pounds, feet, grams, volume. I have no idea. All I know is that the variance is 60. The data spreads from 65 to 125. It's unitless. Now, standard deviation, you bring your units back into it. So when I figure out my standard deviation, I'm going to tell you its first standard deviation is 25 feet left and right of mean or something like that. I'm going to show you an example. So it's important to know that variance is unitless. Standard deviation does have the units. Variance is just the spread of data. Standard deviation is a measurement. Let me see, what did I say it was? The quantity found to determine the range or amount of deviation of a group of measurements. Okay. I know it's a mouthful, and you'll see for yourself what it means here in a second. Okay. Okay. Also, with standard deviation, if you have really good tight data, which means your variance looks more like the red data set than the blue data set, then well, hold on one second, guys. Are you not getting it?
No, it is for some reason the orange letters aren't turning off.
Okay, guys, I'm gonna run upstairs for one quick second. I gotta turn my oven off. I tried to
You're
set my
fine.
son up.
You're fine.
Hold on.
Dinner time in Denver.
All right, I'm back. Sorry,
You're
I have
good.
some French fries in the oven. I thought I could tell him how to turn it off, but he was panicking.
Oh, you're fine. I love it.
All right. All right. So with variance, if you have good data, a good data set, and your variance is small, what that is telling you is you're not really deviating from the same measurement. You're making all these measurements and you're getting relatively the same answer every time, right? So if you're measuring like how much a bag of rice weighs off a factory floor, you want that variance to be really small. You don't want to be giving out bags of rice that some of them weigh 10 pounds, some weigh 9 pounds, some weigh 12 pounds. You want them all to weigh 10 pounds, right? You're selling a 10-pound bag of rice. Now, so the variance in that situation would be really tight, right? If your factory floor is a machine's malfunctioning, it's pouring more rice in, well, then you're going to get high variance. So that's when you see the red data resulting, that means you're going to get some good certainty here that what you're measuring is pretty good. And when it's a really tight variance, then your standard deviation is going to be small as well. So they'll both kind of shrink down, which is what you want. You want really good tight stuff. You are going to get some outliers, and that's going to be because of error, and we're going to get into that. But you want to maintain around that average every time, okay? You want that 10-pound bag of rice to measure 10 pounds, 10.01, 10.02, 9.99, okay? You want it to be really, really, really tight. All right? Is this making sense to everyone? Please, if not, let me know. Hopefully it makes more sense. Sorry.
So far, so good.
All right. Hopefully it makes more sense as we go through the example, and that's right here. Okay. So here's a small data set. we're only going to do a few numbers just so that I'll show you how to do this. There's statistical applications where you can input tens of thousands of points or values into a system, and it'll create all this for you, but we're going to do it by hand to show you how to do these steps. Okay. We only have 6 individual measurements here. Let's say we're measuring those bags of rice. Okay. And we pull 6 bags of rice off of a pallet, and we're going to see if our factory floor is working or not. And we want the bags of rice to weigh 8 pounds, let's say. All right. So we have 6 bags that we pulled off randomly, and we go weigh them. And when we weigh them, we find these amounts of pounds. We have a 10-pounder, a 6-pounder, 8-pounder, 7-pounder, 8-pounder, and a 9-pounder. Okay. First thing you do is you find the average of these. So to find the average, you simply add them up, and you're going to divide by the number of individual data points. 1, 2, 3, 4, 5, 6. So you're going to add up 16 plus 15 plus 17. So it'll be 48 divided by 6. You're going to get 8. So my average is 8. Okay. Which is good. That's what I want. But I do have some pretty small bags, and I have some big bags, right? So in this data set, if I organize these by size, it would be 6, 7, 8, 8, 9, 10. I just want to find the mode and the median in this situation. So my mode, what's the largest repetitive number? The mode is 8. Mode equals 8. Median is going to be the middle number. I don't have a middle here, but I do have 2 numbers that I need to average that are in the middle. So 8 plus 8 divided by 2 is 8. And my average, or my mean, is 8. So with this data point set of 6 numbers, I have a mode of 8, a median of 8, and a mean of 8. So everything's matching up. Okay. So the first step is get your average, your mean. The next thing I got to do is I got to find the residuals of every single one of these. To get the residual, you got to find out how far they are from your mean. Okay. So the way you do it is you do 10 minus 8 equals 2. 6 minus 8 equals -2. 8 minus 8 equals 0. 7 minus 8 equals -1. 8 minus 8 equals 0. And 9 minus 8 equals 1. So now here are my residuals for every point in my data set. I got positives and negative numbers. Okay. Let's add up all these. And when I do, I get 2 plus -2 plus 0 plus -1 plus 0 plus 1. Okay. So this will be -1. I get 0. Let's see. Oh, I know it. I didn't square them. Sorry. I skipped a step. So I have my residuals. And the reason you square them is just exactly what happened to me. I got 0. That would not have worked. Okay. So the reason you're going to square these residuals and then add them up is because you're going to eliminate these negative signs by doing that. Okay. So I square each one of these residuals. So it'd be 2 squared, -2 squared, 0 squared, -1 squared, 0 squared, and 1 squared. Okay. If I do that, I'm going to get 4, 4, 0, 1, 0, 1. All right. I get 4 plus 4 plus 0 plus 1 plus 0 plus 1. Then, so this right here, if I add these up, I get 8, 9, 10. And I divide that by n minus 1. So my data set number, which is 6, minus 1 is 5. So essentially I have 10 divided by 5 equals 2. Right there, variance is 2. Okay? And to prove it, if I were to plot these out, let's see, I may have already done it. Yeah. If I were to plot this out, I see a spread of 2. Okay? It's 2 each side of my mean. So from my mean of 8, if I go 2 to the left and 2 to the right, that's going to be my spread. So I get a variance of 2. It's unitless, like I said before, but this tells me how far left and right of my mean of 8 my data set point is. Okay. So if I multiply this by 2, I'm going to have 4. So no matter what in my data set, I am not going to be larger than a spread of 4. I'm going to be 2 left and 2 right. Okay. So to get your variance, you find your average. Then from the average, you find your residuals. You square your residuals. You add them up and you divide by the number of your data set minus 1, which would be n minus 1. In this case, it's 10 divided by 5, which is 2. So this defines your variance. And by definition, standard deviation is the square root of 2. So the square root of 2, square root of your variance equals standard deviation. Square root of 2 is 1.41. So my standard deviation is 1.41. Now this does have units, and it's going to be pounds, because that's how many, that's what I'm weighing my bags in. Okay. Now that we know our standard deviation, what the hell does it mean? All right. So standard deviation, one standard deviation in this data set, one standard deviation equals 1.41. Okay. That means 1.41 units either side of my mean. That is going to be the spread of my data within one standard deviation of my mean. And I'm going to explain, I think I do, yeah, this 68, 95, 99.7% rule. We're going to get to that here in just a second. But let me outline what this is first. So I have my data set. If you look at the blue screen, I'm not going to redraw it. It's I drew it out perfectly right here. So if I plot out my points from that original data set, which was 10, 6, 8, 7, 8, and 9. So I got 10, 9, 8, 8, 7, and 6. Okay. So here's the spread. My variance was 2 right and 2 left. So if I go 2 units right and 2 units left, I have a variance totaling 4, but they state variance as a distance from mean. So it's going to be 2 to the right and 2 to the left. If I square that 2, square root, I get my standard deviation. So there's going to be, well, there's an infinite amount of standard deviations, but we typically go for the first, second, and third standard deviation. And what those are going to mean are, you have a 68% likelihood that any point in your data set is going to fall within that first standard deviation. Then you have a 95% likelihood that any point in your data set is going to fall within 2 standard deviations. And you have a 99.7% likelihood that any data point in your data set is going to fall within the first, second, or third deviation. And if you look at our data, so we came up through the math with a standard deviation of 1.41. My mean was 8. Okay. If I go 1.41 units to the right and 1.41 units to the left, that's going to bring me to a value of 9.41 and 6.58. So you see these two values, 6.58 and 9.41. It's saying, and this right here is my first standard deviation. So really, just like variance, my standard deviation, it gives me a value, but I have to go left and right of my mean. So really, I'm looking at a range, not of 1.41. I'm looking at a range of 1.41 times 2. So I'm really looking at a range of 2.82. So from this point to this point, if this was 8, I'm going 2.82 units, and that is my range. So this right here is a 2.82 unit range. And I am saying that if you give me any point out of my data set, there is a 68% chance that that data point that you randomly chose is going to fall within here somewhere. Okay? That's the first standard deviation. The second standard deviation is I'm going to go another 1.41 to the right and 1.41 to the left. And that's going to widen my range another 1.41, and it's going to subtract a 1.41.
Hey, Dane, Dane,
Yep.
that 6.58 should technically be 6.59, just so you know, just as a clarification in case somebody goes, how did you get that? So 8 minus 1.41, right? So 6.59.
Oh, good. Thank you.
Yep.
And that's not a rounding either. That's
That's right. Exactly.
Okay.
And then 5.18 to your left there. And then 1082 is your two numbers there.
Let me see. Oh yeah. 5.18 you said?
Yes, sir.
And yeah, and 5.18 and 10.82. Okay. So I've gone another 1.41, which was my standard deviation. Now I have this area, this range. And what I'm saying is, if you give me any data point from my data set, there's a 95% chance that that point will be in this range somewhere. Okay. Then I can finally go to my third, and I'm adding another 1.14, and I'm subtracting a 1.41 and 1.41. That brings me to 12.23 all the way to 3.77. So now I even have a wider range. And then there, I can safely say I have a 99.7% chance that every single point in my data set is going to be within that range. There's still going to be some very far outliers in my data set, but the likelihood of them being within 3 standard deviations is 99.7. Okay. So you just get further and further out of probability and likelihood of a point being within your first, second, or third standard deviation. And remember, when you solve for your variance or your standard deviation, it's only going to give you the width that you go, or the spread or the range you go, plus on the plus side of your mean and the negative side of your mean. Okay. It's going to go both ways. We figured out the variance was 2, and that's fine. But you got to think, it's not just 2 total, it's 2 both directions. So it's really a spread of 4. Okay. For the math purposes, you don't need to know that. You only need to know that it's 2. Okay. Same thing with standard deviation. We solve for the standard deviation, which is the square root of your variance. We come up with 1.41. Well, that 1.41 is going to go above your mean and below your mean. So you're looking for a range. Okay. Does everyone follow this? And if you look, I know our data set only has 6 points, but if you look at it, it is making sense. If you picked out any one of those 6 numbers, there was a 68% chance that it was going to be within between 6.59 and 9.41. And sure enough, they are. Then if you were to go to standard deviation of 2, you had a 95% likelihood that any one of these 6 points would be within that range of here to here. And they were. And then a 99.7 for the third. Okay. Really quick, once again, to get your standard deviation of variance, all you do is you get your data set, you find the average of it, then you find the residual from each point of your data set to that mean or the average. You square those values, you add them up, and then you divide by the number of data points minus 1. That'll give you your variance. Once you have that number, you simply square root it to get your standard deviation. Okay. Variance is unitless and gives you a range. Standard deviation is not unitless. It does have the units of your data set, and it's going to give you the likelihood of a point in relation to the mean. All right. I know it's kind of a mouthful. I'm willing to take challenges or anything, any questions.
Anyone?
Okay.
Got nothing.
All right. I'll take that as a good sign, I guess. It's not very hard math. I mean, to understand it is another thing, but the mathematics behind it is pretty simple. I mean, it's adding and subtracting and multiplying, right? All right. Now, like I said, in any data set, notice even the third standard deviation is 99.7. That tells me that 0.3% of your data still has a chance of not even being within the third standard deviation. Now, why would that be? Well, let's say you were doing you were measuring those bags, and when you were measuring one of those bags, you forgot that your foot was on the scale, and you measured the bag and it weighed 110 pounds. Okay. Well, that bag of rice is going to be an extreme outlier from all the rest that you measured. It's not going to make sense in regards to the rest of the data. So, in that situation, that 110-pound measurement that you made, that's going to be an extreme outlier, and it's going to fall outside that 99.7%. So you're going to have errors that do get introduced into the system. And it's our responsibility to understand those errors, eliminate them, or not let them occur in the first place. Okay. So error, if you think about it as a term, as a mathematic term, error is a measurement value minus the true value. Which is kind of like a residual, if you think about it. Okay. The question here is, what is the true value? Well, in the bags of rice analogy, the true value would be 10 pounds. That's your target. That's what you're really going for. Okay. So your error would be, in that situation, you have a 10, so error equals the measurement minus the true value of 10 pounds in this situation. And you measure that bag to be 110 pounds. So your error in this situation would be 100 pounds. You have a 100-pound error in that case. Okay. So let's go over the types of error. There's some that we can actually correct for, and there's some that we have no control over. Okay. The ones that we can correct for are called systematic errors. And these errors are identifiable. They're typically consistent, and they're proportional. So an example of this would be, let's say, I should be using, I don't know why I went on this 10-pound bag of rice analogy, but I'm going to just keep rolling with it. So I should be using like a survey measurement, but let's go with the bag thing. Okay. Let's say that where this rice is spitting out into a chute to pack these bags, let's say that there's something clogging that chute. Okay. Let's say there's a dead rat in the clog in that chute. All right. So there's not going to be a lot of rice that's being pushed down that chute to fill the bags. So every single bag that you're filling is going to be below the 10 pounds. Every single bag is going to be around 8 pounds, let's say. That would be an example of a systematic error, because you're getting the same result every time. And when you have the same result every time, you can now try to identify it. Why are these bags only 8 pounds as opposed to 10 pounds? So you go through your system and you realize, oh, there's a dead rat clogging the chute. So you pull the rat out and everything's fine, right? So that's an example of a systematic error. And that can occur through your instrumentation, through observations, environmental factors. So like if you're measuring with a steel tape and it's a really hot day, well, that steel tape is going to be expanding with the weather, right? So there's ways to eliminate that error. That would be an instrumentation error. Observation errors, that would be something like someone's reading the bottom wire of a 3-wire level all day long as opposed to the middle wire. Okay. And then there's theoretical errors. So there's different types of systematic errors, but what you need to know is systematic errors are identifiable, and most importantly, they're correctable. Okay. If you can identify what's wrong, then just stop doing it or start doing it. Right. So that's systematic error, and that's what we can correct for. The next one is random error. Now, random error is not identifiable. And if you can't identify it, then you can't correct for it either. But the good news with random error, if it truly is random, then you should be getting 11 pounds of bags of rice, and you should be getting 8-pound bags of rice. It should go in both directions. It wouldn't be consistently 8-pound bags of rice every time. It's going to be heavy bags, perfectly good bags, and then you're going to get some small bags. So when you see the spread of your error with positives and negatives, and it's not consistent, that's a sign of random error. And those aren't identifiable. That's not a rat in the chute. That's something else. That's calibration of the software in your factory floor. There's something else going on there. But the good thing with random errors is they tend to cancel each other out. If you're getting heavy bags and small bags and medium bags, then those heavy bags are going to make up for those small bags, essentially. Does that make sense? So random error tends to cancel itself out. However, it's not going to be perfect. There is, at the end of the day, at the end of your year, and at that rice factory, there is going to be either a surplus of rice or a deficiency of rice, one or the other. Okay. It might not be as bad as you thought all year long, but at the end of the day, you're going to get some big bags and they're going to make up for the small bags and vice versa. So systematic is identifiable and correctable. Random is unidentifiable and not correctable. And the way you can identify them is systematic is consistent and random is all over the place. Okay. And then the third type of error is a blunder. Now, a blunder is a mistake. It's just what it sounds like. So that's if you're doing a level loop and you're supposed to write down 6.58 feet, and then you accidentally write down 8.58 feet. Okay. You made a mistake. You blundered that data set. So that's the third type of error. And those are correctable too if they can be identified. But sometimes they can't. If they're a one-off, sometimes they can. Okay. A good example of a systematic error would be if you use the wrong prism constant one day. You go out and you use your prism and you tell your data collector that the prism constant is X when it should be Y. Well, every single shot you took that entire day is going to be off the exact same amount. So it's simple. You just go in, you change that prism constant. Now every single point of your data set is back to where it should be. That's systematic. It was identified, you corrected for it, and you can move on, right? Does anyone have any question about the types of error? Now, I told you how to correct for systematic. You identify it, and then you can correct it. So there's no propagation of error needed for systematic. Now, there is propagation of error needed for random, and that's what we'll do next, okay? And if you go back to that, if you go, I think I still have it. Yeah, if you go here, you'll see that they go through propagation of error somewhere. Yeah, oh, sorry, right here. Sum, series, mean, and product. Okay, these are propagation of error examples or equations. So you only propagate error for random, and that's what we'll do now. Okay, propagation of error, spreading out the random error. So that's what propagation is doing. It's spreading it out and trying to clear it up by spreading it to all the data points, okay? All measurements have random error, as previously stated. Random error tends to nearly cancel or eliminate themselves, random errors do, but never completely do so. So that, again, that's the 11-pound bags of rice, 9-pound bags of rice. They tend to cancel each other out, and you're going to get an average of 8 still. I'm sorry, of 10 still, but you're still having to propagate that error. There needs to be an understanding of the accumulation and cancellation of random errors introduced into a system. This concept of understanding random errors behavior is known as error propagation or random error propagation. All right, and there's 4 ways to propagate error. And the reason you choose which one of these 4 is by your data, what you're dealing with. And I'll explain that right here. All right, the first one, summation. So summation is when you have 2 different uncertainties being added, introduced to your data. So in this example I give, I'm not going to go into a lot of reading, but so let's take a row team, okay? And this row team, they practice every day, the same river, the same coach, the same group of people, and they can row a boat from point A to point B every day. They've been doing it for 5 years, and they can row a boat from point A to point B, from one dock to another, in 45 seconds. If you were to add up every time they rowed from point A, or every time they rowed from point A to point B, if you were to add up every time that they did it in the last 5 years, you're going to get around 45 seconds, plus or minus 10 seconds. Okay. So they get from A to B anywhere from 35 seconds to 55 seconds. So you can almost guarantee that if you were to take a stopwatch out and time them, their time would fall somewhere in between 35 seconds and 55 seconds. Okay. So they can do it in 45 seconds plus or minus 10 seconds. Now that river, that's the consistency of the row team's ability. But they're flowing. Let's say they always go from A to B, okay? And the river is flowing from B to A. Now that river, it has a different flow rate. And the flow rate for water in that river is 15 seconds plus or minus 3 seconds. So if you were to measure the speed of that water, it's going about 15 seconds plus or minus 3 seconds. So if you were to measure the flow of that water, it would range anywhere from 12 seconds to 18 seconds. Okay. So we have this other factor that we have to consider when we're going to time these rowers. And if you notice, we have two areas where we can fluctuate. We can fluctuate in the ability of the rowers, how fast they can row that day, and we have the fluctuation in the flow rate of that river. And they are not related at all. We have river speed and we have rower ability. These are two different systems completely, okay? When we have two totally different systems, we're going to sum that error propagation, okay? And the way you do it is this equation right here. So you are going to take the uncertainty of one of the errors, of one of the factors. So let's take the rowers first, the rower's ability. They fluctuate within 10 seconds. So it's going to be 10 squared plus, then you take the other system of fluctuation, which is the river, and its range of uncertainty is 3 seconds. So it'd be 3 squared. Then you take the square root of it. So you add the uncertainty squared of each system, and then you're going to take the square root of it. So you're going to add the squares, take the square root. The answer for this is going to tell you, well, the answer here is 10.44. So if I sum the uncertainty of the flow rate of the river and the uncertainty of the rower's ability, I get a total uncertainty of 10.44. So now, if I know the rowers can do it in 45 seconds, and I add and subtract 10.44 from that 45, I get a range of, let me see. Oh yeah, so they go from 30 to 55. Let me see. Finally, the row team can row 1 mile in this situation in 30 seconds. Therefore, they can do it somewhere between, I wonder why I said 30 seconds. Oh, sorry. So, okay, so I found my summation of random error is 10.44. And I measured them. I don't know why I went row at 45 seconds. Give me 1 second here. Flow rate of 15. Oh, yeah. Sorry. I don't understand this part right here. Give me 1 second. Why did I do this? Time. Oh, yeah. Oh, I'm sorry. They're going down. They're going upstream. So if they can row it in 45 seconds, and then they're going to be at most held back 15 seconds, that means they've rowed that river in 30 seconds. Now, from that 30 seconds, I go 10.4 up and 10.4 down. Now I can tell you the range of possibility for that team. And it's from 40.44 seconds to 19.44 seconds. And I think I made a mistake. I think they're going downstream with the river. I've been saying upstream. It should have been down. That's where I'm confused. So they can go from point A to point B in 45 seconds. That river is going to help them because it's flowing with them for 15 seconds. So they can really get from A to B in 30 seconds. Does that make sense? If the water was completely flat, it would take them 45 seconds plus or minus 10 seconds. So let's say 45. But if they go on a perfectly flat day, it's only going to be 45 seconds. If they go and the river's raging, pushing them along, the best they can do is 30 seconds. So this is going to be the best they can do. Now, from that, I have to go my plus and my minus 10.44. And that's how I get a range of 40.44 and 19.44. Okay. So what I'm trying to do in this situation is I'm propagating my random error by summing it. And the reason I can sum this error is because it's two totally different systems. I have flow rate of a river and I have a rowboat's ability or a row team's ability. Okay. Hope this last part didn't confuse y'all. This is the part that matters right here. So I derived at this 30 seconds by 45 seconds of the rower's ability, and I subtract the 15 seconds of the flow of the river that's helping push them along. Okay. So they're going from A to B and the river's going A to B. So if they just sit in the boat and don't do anything, they're still going to be being pushed along, right? Okay. Does everyone understand this?
So 1944 or George threw in there 1956 on your numbers there.
Let me see. It'll be 30 minus 10.44, right? Yeah, it should be 19.56. Is that what you get, somebody?
Yep. That's what George threw in there. Yep.
All right, let me change that right here. Well, I can't. I'm gonna make a note. And what was your other one? Oh yeah, standard deviation is 6.58. I'm gonna keep that up.
And that should be 6.59. Yeah.
Oh.
Yeah. There you go.
All right. Okay, I'm gonna go change those. All right. So that's summation of error. And I can do that because it was two different types of error being introduced into a system. Now, what if that error was the same? What if I don't have a flow rate of a river? All I have is that rower's ability. Okay. And I'm not measuring like I measured that one time they went with the 45 seconds plus the flow of the river. Now this time I'm all we're going to do is we're going to measure that same row team doing it 10 times. So we're going to measure, we're going to sit on the shore and we're going to watch that row team row from point A to point B 10 times. We don't have any river now. Okay. That team can row that distance in, let me see, 450 seconds. Okay. Plus or minus, wait a minute. I'm sorry. It's 45 seconds still, 45 seconds plus or minus 10 seconds. So I sit there and I watch this team row from A to B and I time them for 10 times. I should have 450 seconds of time, right? Plus or minus what? That's the question. So I'm basically going to get an average of how many times they run this course. And the way we do that in this is called an error in series. So you're going to take your uncertainty of 10 seconds times the square root of how many times you watched them row, which was 10 times. And I get plus or minus 31.62 seconds. Okay. So before I even measure this row team, I know that whatever answer I get, it's going to be 450 seconds because I've measured them 10 times. 10 times 45 is 450 plus 31.62 and 450 minus 31.62. So if I get the answer to this and the answer to that, which is 418.38 to 481.62. So when I sit there and I measure this team 10 times, and I know that they can, on an average, do it 45 seconds plus or minus 10 seconds, I know that my range, that when I'm done, it's going to fall within 418.38 to 481.62. So whatever number I get is going to fall in that range somewhere. And the way I know this range is by taking the uncertainty of plus or minus 10 seconds times the square root of the number of observations I made, which was 10, I get 31.62 plus or minus. So I add that to my 450 seconds and I subtract it from my 450 seconds. The reason I can do it this way now is because the error of that team going from A to B, it's only going to be the rower's ability every time. I'm not introducing flow rate, or I'm not introducing paddle size or any other error. All I'm doing, it's the same paddles, the same rowers, the same distance every time. Okay. So that's the same random error. I can eliminate random error by performing propagation of error in series, which is this. So we've done summation and we've done error in series. The other two are multiplication and averaging. So let's do the multiplication one. This is the one that I think is going to make the most sense and is applicable actually to what we do. And I have a good example. Okay, let's say you are given a rectangle piece of property and you're told that this property is 105 feet plus or minus 3/10 and 131 feet plus or minus 4/10. Okay. How would you get the area of this rectangular piece of property? Okay. The formula states you're going to take the length. Let's make this the length and this the width. No, let's make this length and this width. That's how I do it on here. Okay. I take the length, 105, I square it, and I multiply that times the uncertainty of the width, which was 0.4 squared. So I'm taking the length I'm squaring it, and I'm multiplying it times the uncertainty of the width. So I'm flipping it, okay? Then I add that to the width, 131 squared, times the uncertainty of my length squared, which is 0.3 squared. And I take the square root of all that. So when I do this, I get 57.52 square feet. So now I just do length times width of this rectangle, which is 105 times 131. And I get 13,755 square feet, plus or minus 57.52. So if I add 57.52 to 13,755, and I subtract 57.52 from 13,755, I'm going to get a range of 13,697.48 to 13,812.52. So I know the area of this rectangle is somewhere between 13,697 and 13,812. It's somewhere in that range, given the length's uncertainty of 3/10 and the width's uncertainty of 4. So the equation for this is length's distance squared times the width's uncertainty squared plus the width distance squared times the length's uncertainty squared. So I'm pairing the opposite. I'm pairing this length with that uncertainty, and I'm pairing this width with that uncertainty. Okay, I flip them. This is called multiplication of propagated error. Okay, y'all understand this idea? All right, this actually came in handy to me recently. All right, and then the last one is averaging, which is the simplest one. So if you know your uncertainties of, plus or minus 3 seconds, plus or minus 10 seconds, plus or minus 4 seconds in the same data set. So that, let's take those rowers again. If I know those 3 uncertainties, I just add them up. It's basically taking the mean of my uncertainties. So in this situation, it'd be 1317 divided by 3. 17 divided by 3, 5.666. Okay, so my average of propagated error in this situation would be 5.666, given these 3 sets of uncertainties. Okay, so if I measured something and I knew in my system I had this uncertainty for this set of measurements, this one for that, and this for that, and I'm measuring the same thing with 3 different instruments, let's say, I can average that out and get an overall uncertainty of 5.666. Okay, does everyone understand that? And if you go back to this equation sheet, those are the 4 propagated error equations that are needed. Okay, this was standard deviation. I showed you how to do that, and this is the values for standard deviation. Okay, and then we're almost done here. Accuracy versus precision. I know we've seen this, but I like to use the target analogy. So what is the difference between accurate and precise? Accurate is how close you are to the true value. Okay. Accuracy really deals with residuals. The smaller your residual, the more accurate you are. And remember, a residual is how close you are to the mean. Well, the center of a target is the mean of a target. So if you're getting close to the bullseye every time, you're going to be accurate. Now look at now precision. You may not be accurate, but your data set is clustered. Okay. So this is telling me that there's a systematic error here. The scope on your gun needs to be tweaked. If you were to tweak it down and to the right, you would be both accurate and precise. Okay. So a cluster of all the points in one set is precise. Hopefully you can get that precision on the mean, which is the center of this target. But regardless, you are precise in this data set. Now, this data set, I'm accurate, but I'm not precise. This is going to be me flinching when I pull the trigger or something like that, right? This is not a systematic error. I'm shooting the exact same way every time here. This way, I can get it. I'm accurate some of the time, but now I have an outlier. So I'm not breathing right. There's something going on that is introducing that error to the system. Okay. So precise is a small cluster. It has nothing to do with accuracy. Is your data tight? This would be a small variance. And then accuracy is how close I am to the center. Okay. This last slide. So we have uncertainty, tolerance, and accuracy. Uncertainty is a range of possible values within a system. We've been propagating uncertainty here. Okay. When we measured that parcel, we said it was 105 feet long, plus or minus 3/10. So I'm providing you a range of possibility in that distance. I'm saying that length is either going to be 105.3 feet, or it's going to be 104.97, right? It's somewhere in that range. This is my uncertainty. Uncertainty is typically written with a plus or minus. Okay. Our total stations, you'll see it says plus or minus 10 seconds or plus or minus 1 second. That's the uncertainty of that gun. All right. Now tolerance.
Hey, Dane.
What's that? Yeah.
Your tolerance was worth 3/10, not 300s.
Oh yeah, 3/10.
Sorry.
Yeah.
I don't want people to get confused when they're watching this.
Yeah. Sorry.
Nope, you're good. And then 105.3 instead of 300s.
Oh yeah.
Sorry.
Nope. Thank you.
Yeah.
Yeah.
There you go.
Okay. Now positional tolerance, that's a measurable tolerance. That's something that's a predetermined allowable amount that your data can be off. And that is kind of like a gun. Okay. When you buy a 3-second gun, you are accepting the fact that gun can measure an angle within 6 seconds. Okay. Because you got to go 3 one way and 3 the other way. So that is a documented, factory stamped, allowable tolerance to a system. When you buy that gun, you are accepting that tolerance. Okay. And then precisional accuracy, it can be, you can say, you can provide precisional accuracy in relative accuracy or absolute accuracy. So relative accuracy is, I like to use like a map, like mapping. Okay, the measurement of a map positions in relation to each other, or map positions in relation to the true ground. So if you were to create a map, and here's your map, here's your house, and here's a tree, okay? The distance on this map, just the map, the distance from this house corner to that tree is 300 feet, let's say, okay? If I know that distance, then I can also measure out to this well here. If I know that's 300, then I know that this can be another distance, X, okay? So everything is in relation to itself, and it is all correct, okay? Now, compare that to the ground feature. The measurement of a map precision in relation to the ground, the comparison of a map point feature location to a true ground location. So this map may not be in the correct coordinate system. I may be thinking it's in Florida when in reality it's in Montana, okay? The distances I'm getting are still relative within the map, okay? That would be relative accuracy, but absolute accuracy, the northing and the easting of that well is not going to be correct. It's going to be off, okay? It's going to be in Florida as opposed to Montana. However, I do know still, whether it's in Florida or Montana, that the distance from that tree to that house is 300 feet, and the distance from that house corner to the well is X feet, right? So think about it as a map that's not projected properly, okay? It's still accurate within itself. It's relatively tolerant, but it's not absolutely tolerant. Does that make sense? Okay. So I know we went over a lot. I'm willing to get emails or have questions or
right. It gets a little lost sometimes.
yeah.
It's definitely not an easy subject to present over Zoom, but it works out really well. But
do you have the ability to give people these
absolutely. Yeah. So if you want to go through and make your updates, you can share all of them. I have the Dropbox folder that's associated with each week. So when there's PowerPoint presentations, I drop them in that Dropbox folder. So
okay, good. All right.
Sir. Yes, sir.
Yeah, feel free to give I think I gave them to you already, but I'll go make those corrections and give it back to you.
Yes, sir.
All right.
Awesome. Anybody got specific questions they want to clarify or want something on? Anyone?
Yeah.
Not so much, Dane. Not so much.
Yeah.
Well, I do know your stuff gets lots and lots of views, so I know your stuff is of value. So even if somebody has questions during our live sessions, it's always going over well on the replays. So
no, I'm good. I understand. Believe me.
Yeah, right. That's awesome. I don't know where everybody is. Jerry, you got anything to add, Jerry? Nobody's providing feedback.
I just want to say thanks, Dane. I enjoy teaching the heck out of this subject, and once the concepts are learned, then I start playing with their minds about how can we apply this. And
yeah,
you know, it because then the fun stuff happens, you know how.
Yeah, that use a lot. utilizing that prism constant, that's how I do it with my guys. That's how I explain systematic versus random is, that prism constant. And that's something everyone sees all the time.
Yep.
Oh, you only added, 0.23, you're supposed to add 0.31. You know what I mean? And
Absolutely.
yeah, that's always a good one. And then after you know that, then you can start saying, okay, go shoot that manhole in at the exact same spot 15 times, and we're gonna get the mean, the mode, the median. You know what I mean? So that's a true application. And then the angles between things, and you can prove that you do have a 1 second gun, or it's kind of fun doing it that way too. And that's real life applications of it.
It's such a valuable tool for surveying because it allows you to really evaluate the data that you collected and put it to good use. And it also allows you to find that if the data you collected is garbage, you need to go
Yep.
touch your head and figure out why.
Yeah, I know. Another way to express this, and that's a good point, George, is like that best fit line with the fence, like physically showing them that that fence is wobbling, and try to minimize those residuals without even using the word least squared. And then it's kind of like an aha moment, like, oh yeah, we just did least squares by figuring out where we can put this thing, where a straight line can fit in those fence shots.
Well, and for boundary resolutions, you can do best fit of 25 or 30 points. And if you've got 20 of them that fit together real well, you've got pretty good justification for maybe scratching your head on the other 5.
Yeah. Yep. I just did this. I did a best fit curve of a bridge girder the other day. And I went out and I shot the center of this girder. They're building these girders, and then they're going to go transport to build the bridge outside of Aspen. And they wanted to make sure that the radius was a certain amount. So I went out and I shot the center line of this girder, like 10 times. It was only 100-foot stretch. And then I actually scanned the girder, and I showed my guys the difference between the scan data versus my data. And I was only off like, it was like 1,800-foot radius. So it's pretty small radii. And, but yeah, to show them the difference between scan and physically shot in, and like work. And then you could physically see what points I was out of plumb or whatever, and when you eliminate some of my other points that I shot conventionally, those two curves kind of get tighter and tighter together. I mean, we got it within like 100th, it was pretty crazy. But those are all ways to physically show this change, or to show the distance and to show your data set.
That's awesome. That's a great analogy though.
Yeah.
Yeah. That'd be cool.
They weren't happy with the girder radius, by the way.
I'm sure not.
It wasn't my fault. They built the mold wrong for it. So whatever.
Right.
That's what grinders are for.
There you go.
Yeah. Yeah.
Cool. Well,
All
anything
right, well,
else?
thank y'all.
I appreciate it, Dane. As always, I know it's dinner time for your kids, so when.
Oh yeah, I'm good, man. Thank you.
Yeah, of course.
Thanks.
I think I have
Awesome,
one
everybody.
more. Yeah, thank you. I have one more of these. I'll see y'all later.
Awesome. Thanks, Dane.
All right, bye.
Everybody. Bye, guys. Have a good week.
Thanks.